Hello guys, welcome to Ramta Solutions. Welcome to your lesson on rate and extent of reaction. Today we are looking at the factors that are affecting the rate of reaction. So how will we move along in this video? First, we are going to revise collision theory, reminding you what we said in the first video and how it affects the rate of reaction. And then we will look at the factors affecting the rate of reaction. And those factors are 1. Concentration, surface area, pressure, catalyst, temperature, and the nature of a reactant. So these are the 6 factors that are affecting the rate of reaction. Okay, so let's get into it. And I hope you enjoy this, guys. Now, collision theory said for a reaction to occur, reacting particles must, 1, they must collide, right? They must collide, and not just collide. When they collide, they must have enough energy. If you recall in grade 11, you spoke of activation energy. We will expand on this in the 4th video. And thirdly, they must have correct orientation at the moment of impact. Okay? Remember, 1, for a reaction to occur, reacting particles must collide. They shouldn't just collide. When they collide, they must collide with enough energy. And yes, they may collide and have enough energy. They shouldn't just collide and have enough energy. They must have correct orientation at the moment of impact. I think there should be a video that we should make explaining collision theory. Okay, and we will make it specifically for collision theory. Okay, so these are the conditions that must be met. Now, when all these conditions are met, you will have what we call effective collisions. Okay, we'll have what we call effective collisions. Okay, when all these conditions are met, you will have what we call effective collisions. Okay, now while we are on it, collision theory also says that the rate of reaction is proportional to 2 things. Now, when we say proportional, we mean if one increases, the other also increases. If one decreases, the other also decreases in this case, okay? Now, the rate of reaction is proportional to the number of collisions per unit time, okay? It is proportional to the number of collisions per unit time between reacting particles, okay? Between reacting particles, okay? And not just that, it is also proportional. Remember, rate of reaction is proportional to the number of collisions per unit time between reacting particles. The more collisions you have, the faster your reaction. Okay? The more collisions you have, the faster the reaction. Now, secondly, a rate of reaction is also proportional to the fraction of collisions that are effective. Oh boy, it seems I will be making lots of corrections, right? It's also proportional to the fraction of collisions that are effective. So this is how rate of reaction, this is how the collision theory explains the rate of reaction. It says the rate of reaction is proportional to these 2 conditions. Okay? Now also remember, for a reaction to occur, these 3 conditions must be met. None whatsoever should be missing. All these 3 conditions should be met. Okay? All these 3 should be met. Now, let's get into the factors affecting a rate of reaction. Okay, let's get into factors affecting a rate of reaction. So this is item number 2, factors affecting a rate of reaction. So we mentioned that the first, or rather, we mentioned that there are 6. So I'm going to start with concentration, like we started in the scope slide. Yes, it was concentration. So we're going to start with concentration. Now, remember, when we talk of concentration, I want to give you an example. Let's say we have 2 containers here. Please assume that the containers are equal in size, okay? Assume that the containers are equal in size. And then inside these containers, there is what we call a solute, a solvent, which is this white space here. And then these blue dots, let's call them solvents. Okay, oh, sorry, let's call them solutes, not solvent. Let's call them solutes. So this white space is your solvent. Okay, now let's look at this container here. Look at this container here. So what you are seeing here, you are seeing this container, it is a solution of whatever, I don't know. As you can see, you have fewer solutes, and here you have more solutes. So this one here, we will say basically it has lower concentration, all right? It has low concentration, while this one here has a high concentration, okay? While this one here has high concentration, okay? While this one here has high concentration. So everything that we're going to say, remember this diagram here. So now let's talk, oh boy, I should have written this. I'm sorry. I forgot to write 2.1 is concentration. Okay, 2.1 is concentration. So now, when we talk concentration, it applies to solutions, okay? It applies to solutions only, okay? It applies to solutions. So remember, this is a solution of whatever you can think of. For example, maybe you're thinking of your Oros, your squash. If you pour maybe quarter cup of your Oros in your 1 liter water, your Oros will not be the same in this part here as compared to when you pour, say, 2 cups of Oros into 1 liter of water. This one here will be sweeter than this one. Hence, we're saying this one will have lower concentration, while the one that's sweet will have a higher concentration, right? So the solution will be a juice, which is coming from water and the mixing of water and your squash, all right? Cool. Moving on, we're saying that concentration, how concentration affects the rate of reaction. This is what we are explaining. So it applies only to solutions. Now, again, what you need to know is this. I want you to see this. As concentration increases, I'm going to write that down. As concentration increases, okay, there will be more reacting particles per unit volume of solutions. Okay, I will explain with the diagrams we have here. So as concentration increases, there are more reacting particles or reaction. There are more reacting particles. Let me not say reaction, but there are more reaction particles per unit volume of solution. Okay, per unit volume of solution. Okay, per unit volume of solution. So I want you to look at these 2 diagrams. Look at this diagram on the left. There are 3 solutes. So if what we need is for these guys to really dissolve or to react with the water. Remember, the aim is to have a sweet juice. This juice that we will have will be sort of, it's still going to be water, right? But this one here, it'll be sweeter than this one here. showing you that, oh wow, it means now what you see here, as you can see, you have what? You have more particles, right? Remember, you have more particles, and these particles are colliding. Here, what do you have? You have fewer collisions. I mean, there are only 3 particles, but here what do you have? 2, 4, 6, 8, 10. So you have more collisions that may take place. All right? You have more collisions that may take place. Now, as we have said, as concentration increases, there are more reacting particles per unit volume of solution. All right? So what does it mean? This means more particles are closer together, and you can see here, okay? So we say more particles are closer together. Oh boy. More particles are closer together. Okay? More particles are closer together. Right? Now, when more particles are closer together, what will then be happening? This means your number of effective collisions per unit time will be increasing. Okay? So we're saying more particles are closer together, and number of effective collisions, okay? Number of effective collisions per unit time, or you can say per unit volume, it's okay. Per unit time increases. All right, let's go back. So when we look at them here, the collisions that are happening here, they are fewer as compared to the collisions that are happening here, because here you have more particles, and now more particles are closer together, right? So what happens? Remember the conditions. Remember the conditions. Rate of reaction increases when number of collisions increase. When the fraction of collisions that are effective increases. All right. So obviously, when you look at these two diagrams, the fraction of effective collisions on this diagram is smaller than the fraction of effective collisions on this diagram. All right. Hence, we're saying more particles are closer together, and the more they are closer together, the more they can collide. And therefore, we're saying the number of effective collisions per unit time increases. When this happens, what happens? The rate of reaction increases. Oh boy, I like writing reaction as Rxn. The rate of reaction increases. Okay? The rate of reaction increases. So this is how you reason when you get into your exam. Okay, this is how you reason when you get into your exam. You say, okay, when you increase concentration, there are more reactant particles per unit volume of the solution, and more particles are closer together. Then the number of effective collisions per unit time is increasing. Therefore, rate of reaction increases. Now, what if they gave you a scenario where concentration decreases? He would say, as concentration decreases, there are fewer or there are less reacting particles per unit volume of solutions. Fewer particles are closer together, and therefore, number of effective collisions per unit time increases. The result, therefore, is the rate of reaction decreases. Okay, so when concentration decreases, the opposite of all that we have written here will result. Right? The opposite of all that we have written here will result when concentration decreases. Okay? Now, we are then headed to nature surface area. Yes, we are headed to surface area. So with surface area, remember from your mathematics measurements, you measured area of a triangle, of a rectangle, and all that. And then when you got to 3D shapes, you spoke of surface area. So this is not really a new topic. Right? This is not really a new topic. So let's talk about it. Now, I want you to imagine, let's say we have a cube. I want to make a big cube. So I'm going to draw it. Let's say we have a cube. Let me draw this cube. Okay, let me draw this cube. Okay, and then we cut it into smaller nyana pieces. Okay, we then cut it into smaller nyana pieces. Let me try to copy it. Yes. Okay. Oh. Okay. Let me do this. I know it's gonna be bad. It's gonna waste my time as well. Let me just draw them. So let me just draw them. So these are your cubes. Right? These are your cubes. So these are your cubes. So these are your cubes. Remember, we're not drawing to accuracy. So I want you to look at this now. Okay? I want you to look at this now. An example that I'm going to show you is this. I'm going to give you an example of a tablet. If you were to pour a tablet in water for that tablet to dissolve, and you break it down into small chunks, which of the two will dissolve faster? The small chunks will be dissolving faster, right? So this is a small surface area. Okay, this is a small surface area, and this is a large surface area. Okay, and this is a large surface area. Okay, so remember what I'm saying to you. I'm saying if you had a tablet and you break it down into smaller pieces, the surface area will be increasing. All right. So what I'm trying to say here is that, one, as the total surface area, okay, as the total surface area of reactants, okay, increases, what happens? You basically are saying that the number of particles available to react are increasing, right? So maybe let me put it in this way. As the total surface area increases, the number of particles that are reacting will increase. All right? Will increase. I'm sorry, I see I'm casing a lot. I don't know why. So as the total surface area increases, number of particles that are reacting will increase. All right? So now you can compare it to this. Remember, I had said to you, when it's a big chunk, it'll be slower to dissolve as compared to smaller pieces. All right? So now check this out. Number of particles that are reacting increase. That's interesting. Now, what does that mean for us? Oh, so that means more effective collisions. More effective collisions are taking place per unit time. All right? So you have more effective collisions. Let me reduce this case-saving. I don't know why. I'm case-saving. More effective collisions per unit time are taking place. Per unit time are taking place. All right? Are taking place. All right? Now, what happens to the rate of reaction? Obviously, when your effective collisions are taking place, right? Oh, sorry. When you have more effective collisions, what does it mean for our rate of reaction? The rate of reaction increases. Okay? rate of reaction increases. All right? Rate of reaction increases. All right? So what is happening now is this. Remember, we had said that when you have a big solid particle, it'll take long to dissolve it, right? So now, when you crush it, meaning when you make it a powder, basically you will be having more particles, right? You will be having more particles. So basically, particles will be in contact with each other, right? These particles will be in contact with each other, right? They will be in contact with each other. And remember, what we need particles to be closer to each other, and that will be leading to increased effective collisions. All right, it'll lead to increased effective collisions. All right, and therefore, when that happens, when you have increased effective collisions, your rate of reaction increases. All right, your rate of reaction increases. Okay, now the third aspect is pressure. Let's look at pressure. So 2.3, we're looking at pressure. Now, I'm going to give you a scenario again, considering that these two containers are equal. Okay? No, let me not make them equal. Let me say this one. Yeah, let me make the other one smaller. So let's say we had, I will say inside this container we have five. Will 5 work? Okay. Let me say 6 particles in this container as compared to 6 particles. I want to say by length they are equal. Now let's consider these 6 particles in this container. So what you see here is that this one here, basically the volume is, it has a higher volume, right? This one, it has a lower volume, all right? So higher volume, lower volume. So this means this one here must be having low pressure, while this one here must be having high pressure, all right? Must be having high pressure. This is why when you're looking at your pump, I don't know how your pump is. At this level, this is your minimum. The more you go down, this is the higher the pressure, all right? The higher the pressure, as you keep going down, as your pivot goes down, the pressure increases, right? The pressure increases. So again, from grade 11 ideal gases, pressure is indirectly proportional to volume. As pressure increases, volume decreases. So remember now, this one applies only to gases. Okay? This one applies only to the gases. Okay? It applies only to gases. And again, remember what I have said. If pressure increases, volume decreases. If pressure decreases, volume decreases, because these two have an indirect relationship. Okay? Have an indirect relationship. Okay? So, now, when pressure increases, what happens? More molecules are forced closer together. As you can see on the 2 diagrams. Okay? Closer together. All right? Now, you can see on the second diagram that now molecules are closer together. Now, okay, when pressure increases, more molecules are forced closer together, right? And then what does that mean? And more effective collisions. When pressure increases, or maybe I should have said end. Maybe I should have said end. When pressure increases, more molecules are forced closer together and more effective collisions are occurring per unit time. Okay? More effective collisions and more effective collisions. Did I say effect? Okay. More effective collisions are taking place per unit time. More effective collisions are taking place per unit time. All right? I don't know why. Is it because it's cold? I don't know. More effective collisions are taking place per unit time. Right? So this is the effect of pressure. Now going to the fourth item. Remember, guys, the same reasoning that we're using, you're going to use in your exam. Okay? It is not going to be different. You're going to use it in that very same way. Now let's look at the catalyst. 2.4, we're looking at the catalyst. Now, with a catalyst, you know that a catalyst basically is a substance that takes place in the reaction without it being consumed. Okay? It takes place in a reaction without it being consumed. In other words, it does not lose its mass or anything. As long as it's in a reaction, the reaction 1 will, maybe let me address this. 1, what a catalyst does, it increases the rate of reaction. It increases the rate of reaction without it being used up. It increases the rate of reaction without it being used up. So, I remember there are people who are very technical with language. So instead of without it being used up, you can say maybe without it being chemically changed. Okay? Without being chemically changed. You can say without being chemically changed. Without being chemically changed. Okay? Without it being chemically changed. Okay? So, the catalyst, what it does, it lowers the activation energy. Okay? It lowers the activation energy. You still remember what is activation energy, right? From grade 11, minimum energy required to start a reaction, all right? So when you put a catalyst, the energy required to start a reaction will be lower, okay? It will be lower, okay? So now we then proceeding to the fourth item, which is, let's look at it, temperature. We're going to look at temperature. So with temperature, we are going to look at temperature and the kinetic energy. Okay, we are going to look at temperature and the kinetic energy. Okay, so now what we're saying is this. If temperature increases, normally, even in my notes, when I see temperature, I like writing capital T. So if temperature increases, okay, if temperature increases, kinetic energy, allow me to call it EK, increases. Okay? If temperature increases, kinetic energy increases. All right? So, as a result, I think you know now. As a result, molecules collide with each other more frequently. As a result, more collisions per unit time. All right? As a result, more collisions per unit time. Remember what I had said. When kinetic energy increases, molecules will collide with each other more frequently. So what does it mean? In simple terms, is that more collisions will be taking place per unit type. All right. This means more collisions will be taking place per unit time. All right. So when that happens, maybe I should think I took a very big shortcut here. So as a result, molecules collide. I'm going to restructure it. Molecules collide with each other. Okay, molecules collide with each other more frequently. Okay, more frequently. Okay, this will increase or this will cause more effective collisions, right? This causes more effective collisions. Okay, this causes more effective collisions, right? And obviously, when you have more effective collisions, what does it mean? The rate of reaction increases. Okay, the rate of reaction increases. Remember, the opposite, when temperature decreases, kinetic energy decreases. As a result, I should have said more. I don't know why I forgot. So let me fix the statement. If temperature increases, kinetic energy increases. As a result, more molecules collide with each other, or molecules collide with each other. It was okay, in fact. Molecules collide with each other more frequently. Now, what about when temperature decreases? So when temperature decreases, kinetic energy decreases. As a result, molecules collide with each other less frequently, and this causes less effective collisions, and therefore the rate of reaction decreases. Do you see now? I wrote that R what? Rxn. So this is a reaction, okay? As a result, a rate of reaction decreases. When you decrease concentration, a rate of reaction decreases. Okay, why is the rate of reaction decreasing? That's because your molecules are now slower, so the collisions will also be slower and they will be less frequent. Okay, they will be less frequent. Okay, perfect. Now, what we basically trying to say here is this: the higher the temperature, the greater the kinetic energy of the particles that are reacting. Okay, perfect. Now, let's go to the last item. Now, the last item is what is it? It is the nature of roots. Okay, it is the nature of roots. Oh my, sorry. Oh, my mathematics. It is the nature of reactants. I can imagine someone is already saying, nature of roots. Equal roots. Somebody's saying non-real roots. Okay, so we're looking at nature of reactants. Sorry. Now, with the nature of reactants, what we're looking at is this. Remember, guys, substances have different chemical properties and they react differently, right? So substances, let me write it down. Substances have different chemical properties. Okay, they have different chemical properties and they react differently at different rates as well. Okay? And they react differently and at different rates. Okay? And at different rates. Okay? And at different rates. Okay? And at different rates. All right? So, what I want you to look at is this. There are things like, basically, we're looking at the type, strength, and number of chemical bonds between atoms that are reacting. So, these things. So, 1, type, strength, and number of chemical bonds affect the rate of reaction. Okay, and number of chemical bonds affect the rate of reaction. Okay, affect the rate of reaction. Affect the rate of reaction. Let me write proper reaction this time. Okay, so here we're talking of the type, strength, and number of chemical bonds between atoms. Okay, these things are affecting your rate of reactions. So now let's look at reactions between ions. Okay, reactions between I'm sorry, I keep writing this RxN. Reactions between ions. Reactions between ions. Okay, reactions between ions. For example, e.g., sodium chloride and chloride ions and sodium ions. Okay, so these reactions, they will be spontaneous. Okay, they are spontaneous. Okay, so by saying they are spontaneous, that also means they happen faster. Okay, they are spontaneous. Why? Because there are no bonds between them. Right? Why? Because there are no bonds between them. There are no bonds. Oh, guys, I should get used to the fact that I'm writing for you, not for myself. There are no bonds between them, right? And since there are more bonds between them, what does it mean? It means they will basically have effective collisions per unit time, and will therefore have effective, not have effective, they will have many, I will explain this, they will have many effective collisions per unit time. I will explain this. So what is happening is this. When you have ions, what is happening is this. Ions are different to molecules because you don't need to, for a reaction to occur, you need to break old bonds in order for you to form new bonds. So when you have ions, for example, sodium ion and chloride ion, they will form sodium chloride. It'll be quicker to form sodium chloride than to dissolve sodium chloride to sodium ions and chloride ion, right? Because before to break down that sodium chloride, you need to break the bonds between the sodium ions and the chlorine, the sodium atoms and the chlorine atoms. But now, when you have these sodium ions and the chlorine ions, because there are no bonds between them, it's easier to form a new bond. But now, coming from sodium chloride to dissolving them into its ions, it will not be easy. Hence, we're saying the reaction between ions is easy, or rather it's spontaneous. Why? Because there are no bonds between them, and therefore they will have more effective collisions per unit time. What does it mean? This means rate of reaction increases, or it's faster. Okay? This means rate of reaction is faster. For what? Rate of reaction is faster for reactions between ions. Okay? Rate of reaction is faster faster for reactions between ions. Okay? When you react sodium ion with chloride ion, it'll be faster to create sodium chloride. But to dissolve sodium chloride into these ions, it'll be a bit slower, or it'll be slower because you have to break down the bonds. Okay. Now, let's look at reactions between molecules. Now we're going to look at reactions between molecules. I think I was partly explaining this. Okay, I was partly explaining this. So when we look at reactions between molecules, One, what we're saying is this. It's a fact. This one is slower than ions. Why? Why is it slower than ions? Because bonds have to be broken in order to form new bonds. Right? Bonds have to be broken in order to form new bonds. Right? In order to form new bonds. Alright? In other words, bonds of the reactant particles must be broken in order to form bonds of the product particles. Right? So, now that I'm saying bonds have to be broken in order to form new bonds, how does this affect the reaction rate? It slows down the reaction rate. Right? It slows down the reaction rate. Okay? But before that, if we're saying bonds have to be broken in order to form new bonds, what is happening with effective collisions? This means here we have fewer effective collisions per unit time. Okay? We have fewer effective collisions per unit time. And what does it mean? It means we have a slower rate of reaction. Okay? We have a slower rate of reaction. Okay? We have a slower rate of reaction. So, this is us explaining the nature of reactants. So, when you get into your exam, look at the reacting particles. Do you have ions or you have molecules? If you have molecules, their rate of reaction will be smaller. If you have will be slower rather. If you have ions, their rate of reaction will be faster. Okay, guys, their rate of reaction will be faster. And this is, or these are the factors that are affecting these are the factors that are affecting the rate of reaction. And I hope you will ace them in your exam. So this is it, guys. I will see you next time. Stay tuned for the third lesson where we will be talking about the measuring of the rate of reaction. So from me, it's a wrap and bye-bye.